Hi Chase, welcome to another lesson. I apologize for the thunderstorm that's outside. So I just want to show you one thing here at the end of chapter 6 before we move on, and that is example 45. I'm not going to go through it in too much detail, but basically they say sketch the curve. And then they give you y equals x cubed blah 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 blah. Okay, y equals x cubed minus 6x squared plus 11x minus 6. Okay, so I just want to show you now, when they say sketch the curve, what they actually want you to do. And it's most likely that they'll guide you through these points, but you should actually, if anyone tells you sketch a curve, you know, what you should be doing is the following. First, so step one, calculate the 0 points. By the way, this is on page 643. Okay, first step is calculate the 0 points, i.e. the x-intercepts. Okay, how do we do that? You should know from our earlier videos. Let y equal 0 and solve for x by factorizing. Okay, you might have to factorize, you might not, but this is in general. Okay, so that's the first step, you get your 0 points. The second step is to find the critical values. Okay, what they mean by critical values, so find critical values, otherwise known as turning points. Right? Okay, so to do that we find dy by dx and let it equal 0 and solve for x. And remember to get all the values of x and not just one of them, right? And this will then give you, so these will give you a bunch of x points, x1, x2, etc. And you can plot them. Here, when you solve for x, you'll get a bunch of x points, x1, x2, etc. And then remember to sub into original function. Okay, so you substitute it into your y equals whatever in order to get your ordered pairs. So then you'll end up with, you sub in x1 and you're going to get y1. And you're going to sub in x2 and get y2. Okay? So you get the x points, you sub it in to get the corresponding y points so that you can have your turning points. Okay? The next step is number 3. Determine if critical points are minimums or maximums. Minima or maxima. Okay? And how do we do that? Well, remember in the previous thing, we let dy by dx equal 0. So here we do the same thing. Dy by dx equals 0. So generally you would use your answer here. So you've got your function dy by dx equals what, we let it equal 0. Okay. Now we found our critical points, which are x1, x2. Okay. Now that was discussed in the previous video. If we want to check if it's a minimum or a maximum, we use our original function y equals ax, for example, whatever our original function was, and we substitute in a value that's slightly left to the x. So if we've got our timeline, here is x1, we pick a value slightly to the left, so slightly less than x1, and a value slightly to the right. We substitute that into our derivative, and we check whether, so let's call these points x2 and x3. So if we first substitute x2, and we see is dy by dx less than 0, or is dy by dx greater than 0? Okay, and then we do the same for x3. x3 is dy by dx less than 0, or is dy by dx greater than 0? Okay, and then we've got actually four possible cases. So we know that at x1, I'm going to make a table, x1, x2, x3. Okay, so here are our possible cases once we've calculated these. Okay, so we've got all of the values I'm going to put in the table are derivative values. We know that x1, the derivative there is 0, right? Because we solved, that's how we got x1. We solved dy by dx equals 0, and we got our x1. And x2 and x3 are the values for slightly on the left and slightly on the right of the derivative to check what the gradients look like on either side of x1. Okay, so then now we know x1, the derivative is 0. And remember, for x2 and x3, you can choose any value to the left of x1 and any value to the right of x1. So choose easy numbers. Okay, so the cases are, we can have the derivative at x2, we can have it less than 0 or greater than 0. Actually, we can have, let me show you, less than 0, greater than 0, greater than 0. There are four cases. So we can have x2 less than 0 and x3 also less than 0. We can have x2 less than 0 and x3 greater than 0. x2 greater than 0 and x3 greater than 0. And we can have greater than 0 and less than 0. So what this is saying to us is, if the derivative on the left, which is x2, so the derivative on the left is negative and the derivative on the right of point x1 is negative, that means that it's a point of inflection. Okay, it's not a maximum or a minimum. Okay, if the derivative is negative to the left, so negative and then positive, what does that mean? That means that the graph is decreasing and then it's increasing. So you can see that our turning point is a maximum, a minimum. Because it's decreasing, then it's increasing. Okay. Here in this case, if they're both greater than 0, then it's not a maximum or minimum. And it'll be a point of inflection. Okay. So how would that look is something like this. So the gradient is 0 at this point, but the graph is increasing and it's still increasing. So that's this case. And then our last case is if we've got derivative greater than 0 and then less than 0. How is that going to look? Well, derivative is greater than 0. It means graph is increasing. Then we get 0 gradient, and then the graph is decreasing, which means that the point is a maximum. Okay. So this whole thing I'm going through is just a summary of everything we've covered, and it's a summary of how to sketch graphs, just so that's clear. Okay. So you check for minimums and maximums. Okay. Let's see. Okay, next is step 4 is find the point of inflection. And there what we're going to do, oh sorry, I forgot something with our minimums and maximums here. Okay, we've determined if the point is a minimum or a maximum. Then remember, we also need to know the actual point. So we've solved dy by dx equals 0 and we get x1. So that is the turning point, but that's only the x value. So we take x1, substitute it into our original function, y equals blah blah blah, and then we get our corresponding y1 point. So then we've got an ordered pair which tells us exactly where our turning point sits. So x1, and there we get y1. Okay, so then that is the point where our turning point sits, because we don't only want to know what x point it sits at, we need to know the x and y, so we've got the full coordinates of our turning point. Okay, next is to determine the point of inflection. So to determine the point of inflection, we find d squared y by dx squared, and we let it equal 0, and we're going to solve for x, and we're going to get an x point, call it x1. Then once again, to get the y coordinate of our point of inflection, we take x1, sub into our original function, which is y equals whatever, and then so we sub that in for x into our original function, and we're going to get our corresponding y1 point, and then we've got x1, y1. So we've got our ordered pair where exactly where the graph sits. And then the next step is to plot all of those points. So we're going to plot our x-intercepts, and then we're going to plot our turning points, and we're going to plot our what did we calculate? X-intercepts, yeah, and then we can also plot our points of inflection wherever they may be, and then we join them all up, and you've got your graph. Okay, so that is the end of chapter 6. There's a lot of questions, so good luck, practice them, see if you understand. Remember, you can use Microsoft Math to help you draw these graphs and check if you're right and everything. And remember, when you sketch a graph, to label all of the points. So label them x1, x2 with the actual values. So you'd label them 4 and 5 or whatever they may be. So label each of those points, okay? Alright, so the next chapter is chapter 7, which is integration. And this is the last chapter in your book. So we've got like just literally a couple of pages to go, and we are done with your syllabus. And you can finally stop listening to my voice teaching you maths. Maybe I'll teach you something else, but at least there won't be more maths. Okay, so let's start with integration. Chapter 7. Chapter 7 is integration. Okay, so the first section about integration, the book starts off by explaining inverse operations. So I think you should be familiar with inverse operations by now, but basically the inverse of addition is subtraction. So if I take 5 plus 5 minus 5, I'm left with 5. So I did an addition and a subtraction, and they cancelled out. Okay, other inverses are multiplication and division, and then we've got differentiation and integration. So basically what that means is that if I take the derivative of the integral of x, I'm left with x. So the derivative cancelled out the integral. Okay? So that's the concept of inverse operations, and the point that they're trying to drive home here is that derivatives and integrals are inverses of each other. So if I find the derivative of y equals x cubed, we know that that is 3x, so dy by dx will be 3x squared. Okay, now the inverse operation of differentiation is integration. So if I integrate 3x squared, I end up with x cubed. Okay, so basically how they pose it to you in your book is, if d by dx or dy by dx equals 3x squared, find y. Okay, And in order to do that, you integrate and you find out that y is x cubed. They want you to do it in your head. Figure out, okay, if dy by dx equals that, what is y cubed? Or what is y? Okay, and that's how integration works. So, yeah, let's move on and we'll see what we can, if we can find another example. So, let's say I took 6x, idiot. 6x to the 5. Okay, so if I tell you that dy by dx equals 6x to the 5, then what is y? Well, y will be x to the 6, because if we differentiate x by x to the 6, we end up with, we take the 6 to the front and we reduce the power. Okay, so basically the integral of x 6x to the 5 dx is equal to x to the 6. Okay, and that's the concept of integration. Well, that's the that's the concept of an antiderivative. Okay, so I see they don't really go into it too much here in your book, which is really stupid, because once again they're not teaching you anything if they don't explain why you're even doing it. Oh, they go into it later. Okay, so you get two types of different integrals. You get an indefinite integral and a definite integral. So an indefinite integral is when you're trying to find the derivative. So that looks like this, and you'll have a function f of x over here, dx, okay, and you'll integrate that and you'll get some other function, call it, the antiderivative is actually written as f, big F of x, and that's what you'll get, and you'll get a plus c here. Okay, you also, this is an indefinite integral. A definite integral looks like this, and you'll have a to b here of f of x dx, and your answer will be some number, so it'll be a number. So an indefinite integral will give you a function, a definite integral will give you a number, okay, as the final answers. So the first thing that they do is start to walk you through a couple of, I'm just clearing the screen here. The first thing that they do is start to walk you through just a couple of examples of integration. So that's 7.2, and this is all indefinite integrals. So basically they tell you that, they basically give you a couple of integration rules. So dy by dx equals ax to the n, then okay, the inverse is the integral of a x to the n is equal to a x to the n plus 1 over n plus 1. Okay, so this is now an integration rule that'll be given to you in a table, so you just need to be able to use it. So basically, if I say find the integral of 2x to the 5 dx, right? What will your answer be? Well, it says here the integral of ax to the n is equal to this. Okay, so let's follow the formula. A is, so we've got a is 2 and n is 5. So it's very simple. So we've got the integral of ax to the n, which gives 2x to the n is 5 plus 1 over n is 5 plus 1. That gives 2x to the 6 over 6 equals 1 over 3x to the 6. Okay? So that's there's one integration rule over there. The next integration rule, or the next, they call them examples. Yeah. It's not explained very nicely in your book. And I think I'm actually going to skip 7.2. The rest of it doesn't really have that much value to it. Basically, what they're trying to show you, let's try example 6. Example 6. Okay. dy by du is equal to sec squared x. Okay. So basically what they're trying to say is, let's just write this out. The integral of sec squared x dx. Okay. And they're saying, what function y did I have to derive to get to sec squared x? So that's what this thing asks. That's what the integral asks. It says, what function did I have to derive to get to sec squared x? And we know that d by dx, the derivative of tan x, is equal to sec squared x. Okay, so the derivative of tan x is sec squared x. So if I integrate sec squared x, they're inverses. So I get tan x. Okay. Another example is number 14. So it's exercise 7.2. Number 14. The integral of negative sine x dx. Okay. And what is the integral of minus sine x? Well, what function when derived gives sine x? Well, we know that d by dx of, so the derivative of cos x is equal to negative sine x. And remember that if we integrate both sides, so they're inverse functions, so the integral cancels with the derivative, and we have integral of sine x is equal to cos x. Okay, so if I said, let's take another one. What if I said the integral of cos x dx? Well, we know that d by dx, so the derivative of sine x equals cos x. And remember, integration is the inverse of differentiation. So if differentiation goes in this direction, then integration goes in that direction. So the derivative of sine x is cos x, so the integral of cos x is sine x. Okay, I hope you get the point about inverse operations. Basically, the idea is, if I differentiate tan x and I get sec squared x, then if I integrate sec squared x, I'll get tan x, and vice versa. Okay. So that's the concept of inverse functions. Okay. The next section, they talk about the constant term in integration, and that's the plus c. I don't know if you remember the plus c. Okay. So check this out. Section 7.3, the constant term in integration. Okay. If y is equal to x squared plus 2. Now, I hope you understand the concept of this inverse operations. I really hope so. Otherwise, this won't make sense. So, if y is equal to x plus 2, and I differentiate that. So, let's take dy by dx. That is going to be equal to 2x plus 0, right? Because the derivative of a constant is 0. So, that is equal to 2x. Agreed? But remember, okay, so now what happens if I integrate? So I integrate this derivative over here. The integral of 2x dx. Okay, well I know that d by dx of x squared, so the derivative of x squared is 2x, right? So we know that we differentiated x squared and got 2x. So if we integrate 2x, we get x squared. So that's what we're doing here. We're integrating 2x. So that is equal to x squared, right? But here's the problem. We integrated this function over here, right? We integrated our derivative that we took. So we should have gotten back to our original function. But we only got x squared, whereas our original function is x squared plus 2. So that's the problem. When we differentiate this constant over here, it becomes 0, okay? And it falls away. And when we integrate back, we don't know what this constant was. There's no way of knowing it. We get back our x squared. You see our x squared is back. Because that carried on, it carried through, and we had 2x, and we integrated that 2x, and we got our x squared back, you see? But what happened to our 2? It fell away, and there's no way to figure out what this constant was. We just know there could have been a constant there. So that's why at the end of integration, an indefinite integral, you always put plus c. So for an indefinite integral, you always put a plus c there. And this plus c can be any value. So it can be from negative infinity all the way to 0, all the way to infinity. It could be any value, we don't know. We just put it there to show that maybe there was a constant in our function that fell away when we differentiated it. And now that we're integrating, we can't get that constant back and we're not sure what it is. So we just put our plus c there. Okay, so that's just an explanation for why it's there. If you don't understand that, it's actually okay. Basically, the summary is when doing an indefinite integral, right? And that's the integral where there's no values here and here. So if it looks like that and it's got a function and dx, then it's indefinite. And if it's got values here, then it's a definite integral, right? So for indefinite integrals, so the ones with no values, always add a plus c at the end. It's really stupid, but you will lose probably 1 mark on your answer if you don't do it. So that's all you need to really know. Like, this is just a nice explanation of why that plus c is there, but for your purposes you probably don't really care. The fact of the matter is, if you do an integral, put a plus c there. For example, if they say integrate 4x dx, okay, what function when differentiated would give 4x? Okay, well, we know that the power here, oh sorry, that looks weird. The power here is 1. So when we integrate, that power needs to increase. So x squared. But if we differentiated that, we'd get 2x. So the function is obviously 2x squared. Because take the derivative of this, you're going to end up with 4x. Okay? So the integral of 4x is 2x squared. And we just put a plus c. Always just put a plus c after doing your integral. Also, if you don't understand how I got to that value, it's okay. We're going to explain that in detail now. There's actually a very nice set of tables that you can use to do your integration. So don't worry too much. But this plus c must always go at the right as soon as the integral and the dx falls away. So once you've done the integration, you add your plus c at the end for all indefinite integrals. Okay? So the other way to get this is, I did this by inspection. I did it using logic. The other way to get it is, I gave you a little formula which basically said that the integral of ax to the n dx is equal to, what was it? It was, see, I don't remember these out of my head anymore. It's been a long time. The integral is ax to the n plus 1 over n plus 1. Okay? So there is the formula for, so it's the same, remember with your derivatives, we gave you that table where it says if the function is this, then the derivative is this. Here you've got if the function is this, then the integral is that. Okay? And we'll go through a couple of those integration rules. And you'll be given the table, you just need to make sure you know how to use it. Okay? And then it'll be chilled. So let's just do one more example here of this plus c business so you get the picture. Take the integral, so integrate 4 over x squared dx. Now you might be saying, wait, but this isn't in the form ax to the n. Well, it kind of is. 4. Remember that if something's at the bottom of, so it's at the denominator, you can just add a negative to the power and bring it up. So it's dx, right? And then all we have to do is apply this formula over here. Okay? So a is 4, n is minus 2, and we just apply the formula. So the integral is equal to 4x to the n plus 1, so that's minus 2 plus 1, over n plus 1, which is minus 2 plus 1, is equal to, and now you add your plus c, because you see we did the integration, so we add our plus c. Okay, and that is equal to 4x to the negative 1 over minus 1, which is equal to, oh, don't forget you carry your plus c. Okay, it's minus 4x to the minus 1 plus c, or minus 4 over x plus c. And there you have it. So yeah, that is your indefinite integrals, and basically that's just describing your constant term, which is the plus c. So the most important things to take out of this piece are that integration and differentiation are inverse operations. Okay. Secondly, you are going to be given a table with formulas that look like this, and you need to know how to use those formulas. So basically, it'll say if f of x is ax to the n, then the integral of f of x is equal to ax to the n plus 1 over n plus 1. So that's something how your table will look. And there'll be a couple of these, so you need to learn how to use them. And the last thing is always add your plus c as soon as your as soon as you've performed your integration. So you see here in this line I did the integration, so the integral and the dx fall away and a plus c comes in and it stays in for all the steps. And that plus c is there because we might have lost the constant term in the differentiation that we didn't know about. But don't even worry about why the plus c is there. It's not important. You're never going to be asked why the plus c is there. All you need to know is when you do an indefinite integral, you put a plus c at the end and you leave a plus c there, and that's it. That's all you have to do. So yeah. Okay, let's do one more section. Yeah, we can cover one more section today. There's a bit of time. Okay. Okay, so our last section for the day will be, the last section for the day will be section 7.4. That is the sum and difference of integrals, right? And basically what this is like it's a property of the integral. So remember we said that the derivative of a function plus a function is equal to the derivative of a function plus the derivative of a function. Okay, remember how we said that. So for example, d by dx of 2x squared plus x. Okay, we can basically all we're saying is that we can differentiate them separately if there's a plus in between. So we can take the derivative of 2x squared by itself because we know how to differentiate that, and then we can take the derivative of x by itself because we know how to differentiate that, and then at the end we can add our answers together with them. Okay, so in this case 4x plus 1, right? So we differentiated each term separately and then we just added them at the end. Differentiate separately, add at the end. Well, it's basically the same story with integrals. Basically with integrals, the integral of f of x plus g of x dx is equal to the integral of f of x dx plus the integral of g of x dx. Okay, so let's do an example of that. So if I say find the integral of x squared plus 2, right? That is basically equal to the integral of x squared dx plus the integral of 2 dx. Okay, the integral of x squared is, okay, let's use the formula. So the integral of a x to the n, let me write that in a different color just so that we don't get confused. The integral of ax to the n is equal to, don't forget your dx. The integral of ax to the n dx is equal to ax to the n plus 1 over n plus 1, right? So the integral of x squared, we've got a is 1 and n is 2. So the integral of x squared is going to be 1x to the 2 plus 1 over 2 plus 1 plus. The integral of 2 is, well, here we've got a is 2, x is not there, and that is because n is 0. So we've got a x to the 0, which is 1. So it's 2 times 1. So it's still the same form. So the integral of 2 is going to be, I said 2 is a, so we've got 2 x to the n plus 1, and we said n is 0, so x to the 0 plus 1 over 0 plus 1. And don't forget, you did your integration now, so plus c. So let's just simplify. X cubed over 3 plus 2x. And there you go. You did your integration. And don't forget your plus c, because I'm almost forgetting it. Don't forget your plus c when you do your integration. Okay, so that is the sum and difference of integrals. Let's just do one more example. I'm going to write that integration rule, and this is the polynomial integration rule. So the integration of ax to the n dx is equal to ax to the n plus 1 over n plus 1, right? So if I said find the integral of 4x cubed minus 12x dx, we know that we can integrate each term separately, because that's a property of integrals. Integrals, we can separate the terms and integrate them separately and then add the answers at the end. So that is equal to the integral of 4x cubed dx minus the integral of 12x dx. An integral always ends with a dx. So you've got integral, function that I'm integrating, dx. Okay, just so you know. So we can integrate them separately. And again, we've got the form ax to the n, ax to the n, right? So it's a polynomial form. So let's integrate it. A is 4, if we look at our form. N is 3, right? So a is 4, x to the 3, which is n. So let's integrate it, and we end up with 4x to the 3 plus 1 over n plus 1 is 3 plus 1 minus, okay, and we do the same thing here, ax to the n plus 1, so that is 12x to the 1, power there is 1, plus 1 over n plus 1, n is 1, so 1 plus 1. And don't forget your plus c. You did your integration, the integral sign fell away, you put your plus c in, and you carry it for the rest of the steps. Okay, so let's just simplify. That gives 4x to the 4 over 4 minus 12x squared over 2. Don't forget your plus c, it carries down like any other number would. So x to the 4 minus 6x squared plus c. See, I also want to forget the plus c. Do not forget your plus c. You're going to lose 1 mark out of 3 or 4 if you forget your plus c. Don't do it. Do not do it. Okay, then as a last question here, they say more difficult integrals must first be simplified to the sum or difference of integrals. Okay, since the product or quotient integrals will only be done later. So, for example, if they said, so example 17 on page 7-8, we're almost halfway through integration already. Okay, example 17 says the integral of x into x plus 1, x minus 2, okay, dx. How do I integrate that? Because all we know at this point how to integrate is the form ax to the n dx, and we know that's equal to ax to the n plus 1 over n plus 1. You don't have to know this, it'll be given in the table. Okay, do you see that we don't have integral of ax to the n over here? But what if we multiply this whole thing out? Then we could probably have that. So let's multiply. Integral of, let's do the brackets, that's going to give x squared minus x minus 2. You should know how to do FOIL by now, I'm not going to explain. And then we multiply this x in, it gives x cubed minus x squared minus 2x dx. Okay, now do you see that we've got a couple of ax to the n's? We've got ax to the n here, there, and there. but they're separated by pluses or minuses, so we can just do them separately. So this is equal to the integral of x cubed dx minus the integral of x squared dx minus the integral of 2x dx. And now we can just do our integration. So let's follow the rule. We've got a is, in all of these cases, a is 1, except here. Here a is 2. So we've got a is 1 here, a is 1 there, and a is 2 there, if you look at your form. So let's do the first one. X cubed, we need to write it like this, because we're integrating ax to the n, so we use this. So we've got x to the 3 plus 1 over 3 plus 1, okay, minus x squared. So ax to the n plus 1, so x squared plus 1 over 2 plus 1, minus, here we've got 2x to the 1. So now it's 2x to the 1 plus 1. 2x to the 1 plus 1 over 1 plus 1. Right. And we've done our integration, so put in your plus c. And simplify your answer. That's x to the 4 over 4 minus x to the 3 over 3 minus 2x squared over 2, which is equal to, don't forget your plus c, x to the 4 over 4 minus x to the 3 over 3 minus x squared, and always have your plus c because it's an indefinite integral. And there you go. That completes our section on the sum and difference of integrals, or integration with sums and differences. So yeah, hope this video helped. If you've got any questions, as usual, feel free to ask me. And also, when you need to come collect your book to study, please just let me know and I'll make a plan so you can get it. Sweet Chase, enjoy.